So, my name is Carl Baldwin. I've been at DigitalOcean for about a year and a half. This is my colleague, Jacob Cooper. You've been there about a year. We're going to talk about what we've been doing for the last year with public traffic at DO. So this is specifically about putting public traffic to the internet on a layer 3 network. DO is somewhat unique in that among cloud providers, most of them don't take public traffic directly into the VM. We're kind of unique in that when you open up your VM and you look at your interface, you see the public address on the interface. So what we've got to do is we've got to get that public traffic to your VM with that. There's no NAT or anything. A couple other things for context around this project. We needed a little bit better IP mobility than what we had. We'd been stranding IPs, and since every droplet gets a public IP address, we have a lot of IPs. And the value of an IP address in the IPv4 space is ever increasing, and I don't think we'll ever go down. Not for a long time anyway. We also wanted to avoid any more reliance on our global database. We've had a multi-year effort in reducing reliance on our global database and regionalizing data. We didn't want to go there. Kind of wish I could see the slides on the laptop, but so this is a little bit difficult. We also wanted to avoid having to refresh a lot of hardware in our fleet. So we're up to about, I think, 12 regions. No, maybe eight regions with 12, 13 data centers. I don't remember, but we didn't want to have to replace a lot of NICs or replace a lot of top-of-rack switches or spines. Or we wanted to minimize the amount of hardware refresh that we had to do to do this project. And the one thing I wanted to make clear is this is not our VPC offering. VPC is something different, which uses a more what you're used to thinking about with an overlay, multi-tenant over an underlay network. So we started with layer 2. DO has been going since about 2012. We started with a big layer 2 network. And why not stick with that? So there's pros and there's cons. Excellent, thank you. With the layer 2 network. The pros are it was super easy to deploy. Pretty much everything speaks layer 2. You boot up a VM, you get an interface, it speaks layer 2, right? So there's simple integration with both the hypervisors and the droplets or VMs that we put on. The model was that the droplets came up on the hypervisors and they were essentially bridged directly into the layer 2 network. And this was great for relatively small scale. But the reason that we can't stick with this is scale. There's a point where we hit limits and we just can't push past those limits. To be honest, I'm pretty impressed with how large DO has gotten on layer 2 networks and VLANs, but we're getting to the point where things are starting to tip over and causing problems that we don't really want to deal with anymore. Layer 2 networks, they're chatty. I can go to a hypervisor in one of our data centers that's still on a layer 2 network, do a TCP dump, and just watch ARPs fly by as fast as they can come in. There's a lot of chattiness on these networks, and as we want to scale farther, maintain our IP mobility, eventually this broadcast traffic's just going to take over. When there are problems, they affect a very large number of users and a very large number of systems. Oh yeah, I gotta go on the clicker. I forgot about the clicker. Why are we going to layer 3? Well, we lose all the broadcast traffic. It's pretty satisfying. The first time we flipped a data center over to having public traffic all over layer 3, I did that same TCP dump on a hypervisor, and there were just crickets. It was it quieted down the network very effectively, and it was pretty cool to watch. The layer 3 approach is much more scalable. We're not limited by MC lag between the TORs and the spines and the cores, where you only have the possibility of 2 nodes of redundancy. Now we can scale out to 3, 4 nodes of redundancy in the class fabric. Things are highly redundant. The blast radius is contained. When things go wrong, we can isolate that to a faulty device, remove it, replace it. Troubleshooting's a lot easier. So we're pretty sold on layer 3 networks. So how do we get there? Clicker. So we started by building out a layer 3 fabric. IP fabric with class topology. We chose to use BGP in eBGP in the data center, and there's an RFC about using eBGP in large-scale data centers. But this came at a cost. It is more complicated configuration on networking devices, and we had to develop some automation around this to get it right. So now that we have our layer 3 fabric in the data center, how do we get our public traffic onto it? So we don't want to lose IP mobility. In fact, we want better IP mobility. So we have a host route per droplet. Remember, every droplet has a public IP address. And sometimes, too, if you get a floating IP and stick it on a droplet. So what this means is we have no possibility of prefix aggregation up to the data center edge. So we have many, many host routes, hundreds of thousands of host routes in a data center. So how do you route this through an IP fabric? Well, one way you could do it is get bigger, more expensive devices, things that can hold all of those routes inside of its routing table in the fib. But that's not what we wanted to do. We wanted to actually get better scalability with cheaper hardware. And another way to go about this would be full encapsulation. Put the public traffic on an overlay and route it over the IP fabric as the underlay. But we weren't quite ready for that for a number of reasons. And we're still working toward that. But we have issues with older NICs, older hardware. We haven't had the time to develop the gateway devices that would do the encapsulation at the data center edge for us. So we're not quite ready for that. What can we do in the meantime? Show you this later. So our answer for that was to use the capabilities that we already had in our switches for doing MPLS. MPLS is just a way for us to protect our spines and our TORs and those smaller, less expensive switches that don't have the fib capacity for all of the host routes that we're throwing around the data center. It allowed us to create label switch paths to each hypervisor and route the public traffic over those instead of pure IP as we work toward a better, more scalable solution in the future. So this is a little diagram of how we've used BGP to signal all of this in the data center. It may be a little hard to distinguish the blue from the the tealish color. But on the underlay, we use BGP-LU. BGP-LU adds an extra NLRI to each hypervisor route, which allows us to signal a label switch path through the data center from the cores down to each host. And then the blue layer, the thicker lines, that's actually a second BGP layer that carries the host routes for each of the droplets. And those are sent to a route server, which aggregates them and then sends them up to the core. So the core routers, those are still a little bit beefy, a little bit expensive, but they have the fib capacity to hold all of the host routes for every droplet in the data center right now. So now let's talk about what's in the hypervisor. And this is where OvS comes into the picture. So at DigitalOcean, there was a talk yesterday explained how we do our data path. And so I won't go into that again, but we have a heavy investment in OvS as our hypervisor data path. We put firewall, floating IP, VPC, handling public addresses, everything's in there in OvS. It's been an advantage for us because it gives us all the control that we need to do what we need to do. And in this specific case, and Jacob will talk about this, we built parallel data paths for layer 2 and layer 3 so that packets could traverse either data path at the same time. And this was key for us to get a seamless pivot from the VLANs layer 2 to a layer 3 network before we actually shut down the VLANs. So what were the challenges we had? Open vSwitch has switch in the name, right? It's generally associated with connecting to layer 2 networks. There's a built-in bond implementation. So one thing we wanted to do initially was to take layer 3 all the way down to the host. We wanted this picture on the top where each hypervisor has an independent link up to 2 different TORs where we put a /31 transit subnet on there, and we use ECMP. But we weren't quite able to get there. It was a little tricky. So what we ended up with was we still use bond 0 that's connected into our BR0 bridge in OvS, and that runs LACP up to the 2 TORs, and the 2 TORs are connected with an inner chassis link. And then inside of the rack, we run a VRP gateway on the TORs on a /20, 25 or 26 network, depending on the rack. So this is a little bit of an impedance mismatch getting into an L3 network. There's some interesting scenarios where if a link goes down, some interesting things happen. For example, if a leg from the hypervisor to the TOR goes down, BGP still has a way to talk to that TOR through the other TOR and the inner chassis link. And so the routing protocol has no idea that link has gone down. And so that hypervisor is still advertised as reachable from both top rack switches. I did an experiment trying to get ECMP to work with OvS, just using an OvS group. And it kind of worked in the static configuration. And in fact, it worked just fine. It actually performed very well. I used a select group with a DP hash. And the problem that I ran into was when you hit failure modes, you really need feedback from the routing protocol to decide what to do with your two links. It isn't just about whether the link up to the Tor is still active or not. There may be other factors in choosing whether to turn off a link or take it out of the ECMP group. So we have a little more work to do there in the future. I'll hand it over to Jacob to talk about how we pivoted our traffic over to L3.
Thanks. So here we have the network architecture for our data centers. Up along the top, you see the class topology nodes. This corresponds TORs. And then we have two types of servers. We have our hypervisors and our route servers. So on the route servers, we have Plinko, which is linked into Bird. Also, that advertises, that aggregates all of the routes from all of the hypervisors. And that's why we named it Plinko. Well, Carl named it Plinko. But all the routes come up and down from Plinko. And then from the hypervisors, we have also Bird running as the router daemon that picks up routes from the hypervisor itself. Then I'll talk about, which also obviously OvS runs on the hypervisor. We have three different services running on the hypervisor to enable this. We have HVFlow, which was discussed a little bit yesterday, that actually injects OvS flows for each droplet. And also it writes some metadata into OvS DB for IP addresses for droplets, so, which are then picked up by announce. So then announce-D takes those addresses and then announces those to all the way up to Plinko and then up to the cores. Then we have respond, which acts as a proxy to respond to ICMP, ARP, and NDP requests of the droplets so that the droplets still think that they're on the layer 2 networks. Let's talk a little bit about the pivot itself. Going from L2 to L3 while droplets still have connectivity is kind of like changing the wheels on the bus as it's going down the road. So, and we didn't want to evacuate hypervisors or even the entire data center when we did this. We want it to be seamless, even on the droplet. So here we have legacy L2 data path and a simplified version of the OvS flows or tables that we use and a description of the flows. So we have packet classification that matches per droplet fields such as IP, MAC, port to the droplet itself, and then do L2 rewrite, tagging or shipping VLANs, and then we also do things like user firewalls and VPC. Since we were able to implement, we use this existing table structure to implement a parallel L3 data path. This allowed us to add these flows without disrupting L2 prior to the traffic pivot, so which I'll talk about in a minute. L3 flows are also flagged so that we can easily remove these if we need to revert back to L2. It was important for us. So talking a little bit how we extended the table structure to include L3. In the packet classification table, we essentially hijack packets going to or from respond. Then otherwise, it's pretty much the same as L2. Matches on port, MAC. And then during the L2 rewrite, we actually match on L3 specific VLAN that we use, or the special MAC address that Respond uses when responding to our per ICMP messages. Then the other tables. And then the actual pivot itself, going from legacy L2 to L3 backfill, our first state within the pivot. We install those L3 flows that are dormant at the beginning. We also install the L3 services and configure the fabric to create that L3 specific VLAN and other configuration that's needed. Going from L3 backfill to L3 egress, we enable the reachability announcements on the core switches already during L3 backfill. OvS DB has all of the IP addresses for the droplets, and those are aggregated by announce, but they're in a no announce state, essentially. Those are then enabled so that you have ingress traffic, the southbound traffic going over the L3 network. Going from L3 ingress to L3 egress, we install flows to redirect ICMP, NDP, ARP messages from the droplets to Respond, so they get that special MAC so we can identify northbound traffic. We also trigger GARPs from Respond to the droplet to help their ARP caches flip over to use that special MAC address. And that same MAC address is used for any ARP entry within their cache.
Thank you very much. User experiences are some of my very favorites because often I'm used to only getting bug reports from users, and it's always great to see the success stories as well. We have time for one question. Would anybody like to ask one? Yep.
Hi. You just mentioned about layer 2 scalability issue, right? When you see the up broadcasting. So, but I also see you have this up responder also implement even for the layer 3. So how about doing the same thing, up responding in OvS for the layer 2 network? Do you still see any difference or still any challenge for the scalability?
One of the big factors there is those ARP messages never hit the network. They never go outside of the hypervisor, since Respond actually lives on the hypervisor and responds to all the messages on the hypervisor. So, and that way we scale the actual fabric.
All right, let's